Okay, before we do example 5, they're giving us a definition for bounded monotonic sequences. If it's monotonic, then it's either non-increasing or non-decreasing. And if it's bounded, it has a place it can't go past, so that would definitely have to converge. So looking at example 5, drug doses. Suppose your doctor prescribes 100 milligrams dose of antibiotic to be taken every 12 hours. Furthermore, the drug is known to have a half-life of 12 hours. That is, every 12 hours, half of the drug in your blood is eliminated. Find the sequence that gives the amount of drug in your blood immediately after each dose. Okay, so what do we know? We know we are starting out with 100. And they're going to use D for dose. Dose 1 is 100. Dose 2 would end up being 100 plus half the dose, or 50. And then it would keep going from there. So we could say that D sub n plus 1 would be equal to 0.5 of whatever I'm on, dose number that I'm on, plus the initial 100 that you're taking. So that would be my function for that. Part B, use the graph to propose the limit of this sequence. That is, in the long run, how much drug do you have in your blood? So if you start plotting this, and if you start plugging numbers in, you'll see what's happening here, because D sub 1 is 100, D sub 2 is going to be 150, D sub 3 is going to be put in 150, half of 150 is 75, plus 100, that's 175, and it doesn't take you very long to realize that it never goes past 200. If you do several more of these, you'd get it. So by the graph would start looking like this. We have our initial one at 100. And so we have a dot here, and then we'd have a dot here, and then a dot here, and then it's going to just bottom out right there. So it never exceeds 200. Part C wants to know, find the limit of the sequence directly. So they want us to take this formula and figure out what the limit is. So we're going to write the limit as n goes to infinity of D sub n plus 1 would be equal to the limit as n goes to infinity of 0.5 D sub n plus 100, which I could then write as 0.5, the limit as n goes to infinity of D sub n plus the limit as n goes to infinity of 100. And then we're going to say, well, let's call the limit L for the initial side, the left-hand side. So this answer right here would become L. This would then become 0.5 L plus 100. Solving for L, we would get 0.5 L equals 100, so L equals 200. So now we've proven it. And that's example 5. Okay, we're going to look at convergence and growth rates for number 6. And we're looking at part A, and we have this sequence here, natural log of n to the 10 over 0.00001n. Now, I could rewrite that as, I'm just going to forget about the little braces here for a minute, but I could say that this is actually 10 ln of n over 0.000, there are 4 zeros? Yes, n. Okay, the numerator is a constant multiple of the sequence natural log of n, but the denominator is a constant multiple of the sequence n. Well, n definitely grows faster than the natural log of n. So, because natural log function grows rather slowly. So in this case, this would converge. The bottom is going to grow faster. If the bottom grows faster, then the thing is going to converge to 0. And I'm going to put because n grows faster than natural log of n. If we look at B, the sequence says n to the 8 natural log of n over n to the 8.001. Okay, looking at the theorem they've given you, they've made a little statement about this. It says if you have ln to a power of n, it grows slower than n to the p, which grows slower than n to the p natural log of r to the r of n, which grows slower than n to the p plus s, which I keep making greater than or equal to's, which grows slower than v to the n, because n is going to infinity in this case, which grows slower than, oh, I'm not able to fit it, n factorial, which grows slower than n to the n. So they've given us a little order here. So if we look at the problem, P would be 8, R would be 1. Yes, because there's not an exponent on it. And for the numerator, and the denominator is n to the p plus s. So according to the theorem, the n to the p plus s grows faster than the n to the p ln to the r of n. The bottom's growing faster than the top, so this also will converge to 0. And then part C. N factorial over 10 to the n. Okay, and again, if we look at this rule, you have n factorial grows faster than any exponential function except for n to the n. So the numerator is going to go up much faster than a number to the n. And so since the top is growing faster than the bottom, this is going to head toward infinity. And so we have to say that this is diverging. Yes. All right, so just remember the biggest thing on this is factorials outstrip powers all the time unless that power is n to the n. If the base is the same as the power, it's going to win. So that's done with number 6. All right, for example 7, we're using the limit of a sequence, which that definition is almost identical to the definition of a limit. And so what we're trying to do is we are trying to find, they're giving me limit as n goes to infinity of n over n minus 1 is equal to 1. And we're given that epsilon is equal to 0.01. Find the value of capital N that satisfies the conditions for the limit definition. Okay, so I'm going to start out with a sub n minus 1, because that's my answer, which will be equal to n over n minus 1 subtract 1, which would be the same as common denominator be n minus 1. If I change the 1 to n minus 1 over n minus 1, I end up with 1 over n minus 1, and that has to be less than epsilon, and epsilon is 0.01. N's got to be greater than 1, so the absolute value can be removed, so I don't need that anymore. So all I'm working with now is 1 over n minus 1 is less than 0.01, which I don't want to write like that. I want to write it as 1 over 100, because we have a rule that says we can flip the whole inequality over, but when we do that, it flips this. And then this would be 100, and so when I add the 1, n has got to be greater than 101. So that was part A. Part B, prove that the limit goes to 1. Okay. So now we're trying to find out that they're given any epsilon. greater than 0. We've got to find the value of n that guarantees that this will work. So if we start out with n over n minus 1, subtract 1, less than epsilon, which changes into 1 over n minus 1 less than epsilon. Solving this for n, flipping the whole, that's supposed to be an epsilon, flipping the whole thing over, we get n minus 1 is greater than 1 over epsilon, which means that n has got to be greater than 1 over epsilon plus 1. So as long as we know that epsilon is greater than 0, it will work where capital N is greater than 1 over epsilon plus 1 to be sure that the terms of the sequence are going to be inside that limit of 1. And this concludes section 10.2.